Differential equations are used when the most important thing about a system is how it changes, not just what it is at a single moment. Speed changes, temperature changes, populations change, signals change. In all of these cases, the present state doesn't directly tell you the future. What tells you the future is the rule for how the state changes right now. That is exactly what a differential equation describes. It links a quantity you care about to its rate of change. In plain terms, it says, given the system as it is right now, this is how it will start changing. Ordinary equations describe static relationships. For example, a line tells you how one number depends on another. Differential equations describe processes. They tell you how a system moves forward step by step. Many real systems don't come with a formula for their future position. They only give you a local rule, like forces causing acceleration or temperature differences causing heat flow. Once you combine that rule with where the system starts, you can predict what happens next. Same rule, different starting points, different outcomes. That's why one differential equation can describe many situations. This is why differential equations show up everywhere. In physics, forces lead to equations for motion, vibrations, waves, and electricity. In engineering, they describe circuits, control systems, and structures responding to stress. In biology, they model population growth, the spread of disease, and how drugs move through the body. In chemistry, they track reaction rates and diffusion. In economics, they describe growth, decay, and feedback in markets. Importantly, you don't always need an exact formula to use them. Often, the key questions are qualitative. Will the system settle down or blow up? Will it oscillate? Is an equilibrium stable? Differential equations answer these questions even when exact solutions don't exist. In practice, computers solve most differential equations numerically, advancing the system forward in small steps. That is how simulations work, from weather forecasts to engineering design. The core idea to remember is this. Differential equations are the mathematics of change. They describe how small, local rules of change combine to produce large, global behavior over time and space.